normally, this is what you're learning, and this is also the case in lower layer, data link layer. Flow control planning window version of flow control. If an X3 is received, that means number 3 is acknowledged. That then means that the window is shifted to the right. In TCP, that's not the case. I can acknowledge data, because this, but then I can do so by set the window size so that I do not open up new space. So sending an acknowledgement does not imply a permission to send data. That's new. Yeah.
So, which means the window can exhaust it.
That's right. And therefore, what happens there is you can set it to 0 and then you have to reopen it.
Okay.
I'll have examples. Yeah.
So when the receiver sends the X back, the window size is 1 less than before because it's not being moved. Would that be correct?
If you acknowledge data, it depends on the second number. Yeah. If I want to have the window shrink. If I want to have the window shrink, then I would kind of acknowledge data, but then reduce the advertised window size. So I have to do it in a smart way. Why is this done? Because these numbers actually, they're not coupled together. The first number is I want to acknowledge data as quickly as possible. Otherwise, I trigger retransmission. The second number here is, this is the buffer size of the receiver. It is what it is. The receiver, if it doesn't have more buffer, it wants to communicate to it. Now, here, these two are decoupled. On the one hand, the buffer size, so the buffer size here happens at the center, kind of here. This is here the center, this is the receiver. The receiver has now, let's say, 4,000 bytes of data available. The sender here, so you're sending here, if half of this is occupied, you're sending here win size equal to 2,000 back. Now, this data is then, so how does this occupied data, how does this get out? Depends on the application program getting it out. Yeah, so this is something that is not in the control of the sender. So if here on the receiver side, this data is not passed to the application, this just fills up. So what you normally would do if you don't have this, you would not send acknowledgement. But then if you're doing this, you trigger retransmission. Yeah, so that's the whole idea behind it. Yeah, it's not so far away from what you learned, but it's a little bit of step up. So this is the picture. If you understand this, you completely understand TCP window flow control. I already put this down here, yeah? So the sliding window. Think about this as this is being the sliding window. The window that slides. This is the number of sequence numbers. Yeah, each byte is a sequence number. So what we have is the size. This is the size of the sequence numbers that the sender is allowed to send. That's the open window. It's called the advertised window. This is the advertised window is set by this number. Yeah? So what it means is at some point this window is set to this value because this here being the sender has received a packet where the X number was set to 3 and the window size was set to 6. Set by the sender. Now, of these, so now in this state here, the sender is allowed to send 3, 4, 5, 6, 7, 8. Of these, the sender may have sent already some. So this is here the part with this are this is the sequence number space, the part of the window that has already been used up, but it has not been acknowledged. So, of the advertised window, the part that has not been sent, that's the usable part of the window. This is the this side, the right side of the window cannot be sent. On the left part of the window, this has been both sent and acknowledged. So what it means is every acknowledgement moves the left side of the advertised window. The acknowledgement plus the window size moves the right part of the window. Yeah, this value, this is here the X number plus this number minus 1. That's the right part of the window. That's exactly this one here. This is the right side of the window. And these dots in the middle, well, that has, the sender has to keep track of. Yeah, what hand it sends. And what's the last number that it has sent. And that's pretty much it. So now you can just, get the sequence numbers. Yeah, so in this setting here, so let's see, the sender transmits byte 6. What's happening? The usable part of the window shrinks. Do you see it? Do you see this one here? So we're starting here at, we have 1, 2, 3, 4, 5, 6. This is the picture we saw before. Yeah? Advertised window goes from 3 to 8. Usable part is 6, 7, 8. 6 is being sent, which is, that's the next byte being sent. Have in mind, this is for illustration. If you have a lot of data to send, you don't send one segment per byte. You send as many bytes as you can. So this one here is like LNet. So what is happening here? Well, if byte 6 is sent, then the usable window shrinks. So what you see is then this. Does it make sense to everybody? Yeah, the usable function. So then the next piece is the sender here receives now an acknowledgement with act number 5 and window size 4. Which means the acknowledgement number, you're taking this number here, act number 5, the left part of the window, plus window size is 4, 1, 2, 3, 4. So that becomes the window. This number here, of course, does not change because it's behavior of the sender, not it's dictated by what the sender is. So then we're here. So then something is received, act number 5 and window size 6. So what's happening here is, if this is received, you can get some candy. We still have some candy left, not much, but just a little bit of Halloween candy, if you want. Then act number 5 and then window size 6. 1, 2, 3, 4, 5, 6. Opens up the window. Yeah. Everybody go to this. Opens up the window. Here we are. And when does this happen? When does the sender sense this? Well, this is now dictated by the behavior at the receiving side. Yeah, so you open, the receiver opens a window. What happens here is, compared to the previous one, you're not acknowledging new data. There's no new data acknowledged. The only thing that is happening is the window size is open. So this is a behavior that is triggered at the receiving side. The data has to pass to the application, freeing data. Now the receiver sends an acknowledgement. And of course, this is mixed in with all the other rules with delayed acts. Yeah, so everything is thrown together. Yeah, so you're delaying your act, you're doing what you have to do, but this is the window side that would be sent at this point. Yes.
You did mention delay that, so we're going to ask if the sender keeps sending because it's, the previous segment.
Yeah. So everything I'm saying here holds, and it holds at the same time. Yeah. So this is here the issue. We're having all these things. The implementation is combined into one blob of code. So everything takes place, which is not hard. Yeah, you only need to send acknowledgements, and they serve multiple roles. Yeah, these are not all the roles. There is more. Yeah, but the acknowledgements are the control information. So that control information, you try to, the designer of the protocol tries to extract as much information from it as possible, tries to use it for as many purposes as possible. So that's the whole idea behind this. It's really not have in mind nothing that nothing is disabled. There's no complication. Just all running in conjunction. Yeah? But if you see this as a block behavior, it looks like random. Yeah? It looks like a very complicated process. In fact, there's a certain few mechanisms that take place, and when you observe it in conjunction. What the lab exercises do, they just set up so that they try to separate this phenomenon as much as possible. But that's by lab, by design of the lab. All right, got this, the sliding window. Good. All right, so here we see there's actually a no-no here. So what's happening here is we have an advertised window from 5 to 8, 7 and 8 can be sent. So now the acknowledgement arrives at number 5, window size 3. So what happens here? The receiver shrinks the window, and actually reduces the usable window. And that is something that should not be done. Why should that not be done? Kind of not good. Why?
Because the sender might have sent the 5 to 8 already.
8 might have been sent. Yeah? So what's happening here is, what if this dot here is just, the receiver has no idea about this, where this line is, what the sender has already sent. So if I tell you, you should not send this data, but if this dot here is over here, kind of if the usable window is 0, meaning the receiver had already sent, the sender has already sent from 5 to 8, so it cannot send anything anymore. Then it receives this, it essentially gets information, you should not have sent 8. 8 is illegal. Yeah. Well, that's not good behavior. So what should happen is, you should shrink the window. If you want to do it, shrink it from the left, roll it from the right. That's what that does. When it says should, that's what it means. Yeah. So there's no hard rule against it, but it's not good behavior, because then the receiver could say, well, if the receiver keeps track of what it has to acknowledge, it can get 8 and says, well, this is out of my scope. And actually, this is a situation that should not really happen. What it means is it had a size to take, it has this window size set to receive these numbers. All of a sudden, space has disappeared. Look at that. If you're thinking about the old size of the window is the buffer available at the receiver. And this behavior should not happen. Somebody then stole buffers away from the TCP connection. So see that if you're thinking about what can get this, that's that. All right. So here are some examples of how this looks like. Sender to the receiver. This is the time moves down here. So this kind of on a higher level scale, having the receiver buffer in mind. So here you're seeing that the window size is set to 4K because that's the receiver buffer. That's a good thing to have in mind. Window size is the receiver buffer. The sender sends 2K. This is all here in K. Let's say K is 1,000. Yeah. 2K sequence number 0. It's occupied. It then says, well, no, it's not 2,000. It's 1024. So it sends ACK 2048. Then the sender sends 2 more, sends 2,000 bytes more. Here the buffer fills up at the receiver, which then causes the window size set to 0. But still, the all received bytes are acknowledged. Yeah, kind of a vanilla sliding window flow protocol would not send an acknowledgement here, because the vanilla protocol assumes that data is being taken out. Here that's not the case. So what happens in this state here? The window size is set to 0. Actually, from this point on, the sender cannot send more data. Here, the window size is explicitly set to 0. So the receiver is blocked during this time. Now, if this is the case, if the window size is set to 0, then So this is a situation where the sender and receiver is blocked and undesirable. If then data gets released at the receiver, the sender should send acknowledgement. Actually, in a state like this, TCP has a rule. If the window size is set to 0 from the sender side, the sender is allowed to send once in a while a 1-byte packet. Why is that? It is there to trigger an acknowledgement. And so the sender can force acknowledgements from being sent if the receiver implementation does not do it. Yeah, so the sender is allowed to send 1-byte packet even though it is blocked officially, can violate that. Yeah? But kind of these are, we don't, there are many details to TCP at this level, so we don't, if that be interesting or not. This is something that, what is important is to have this model in mind. All right, that's that. So next thing I want to cover is error control. Error control, it's about retransmission. So what is, so TCP maintains a timer. What's important to have in mind is there is one timer per connection, not one per packet. And of course, what TCP, for a couple of years, that was longer than one. There was a timer per packet. So there was a timer for a packet. No, it's a timer per connection, one timer. The timer is started during a transition. Timeout causes a retransmission. Setting a timer, RTO, retransmission timeout. Now, this is something that we have to deal with. So tomorrow I talk about congestion control. TCP couples error control and congestion control. It's more important for congestion control. In the sense that whenever an error occurs, whenever a timeout occurs, it assumes it's caused by network congestion. It doesn't assume there's a random error. It assumes there's a timeout. That was because the network is full, and that causes, so any retransmission kicks in congestion control algorithms, which we discussed tomorrow. So today, no congestion control, only error control. The issue with dealing with TCP is how to set the retransmission timeout. If you're having a TCP sender and receiver, it could be on the same computer. In fact, very often they are on the same map. The distances are very small. It could be that the sender and receiver are halfway around the world, one of them using a very lousy connection. So there is no one-size-fits-all for the retransmission value. It can be anything between a sensible value, can be anything between 10 milliseconds up to seconds. So, because if you're having a retransmission, if your timer is too small, if you timer out too early, you're sending unnecessary retransmission, causing out-of-order delivery. That stuff's happening. You're assuming, because it's coupled here, you're assuming the network is congested, even though the network is not congested, it's just your retransmission time is respected. If you're sending data, you're setting the retransmission timer for too long, you're degrading performance. If you're having local area connections, you are setting it, you have your retransmission timeout is at a few seconds, something gets lost, you're waiting a second, throughput is can be severely degraded. So how does TCP solve it? And this is something that transport protocols have to deal with. Again, if you're talking about error control at the data link layer, on a link, everything is pretty much deterministic. You know how long the wire is, you know how long things will take. And it's knowledge, knowable. In TCP, you don't know. So what's the solution? It has to be set dynamically. So here, the setting of the retransmission timer is a big part of the retransmission scheme. The retransmission scheme itself is just go back N. If there's a timer, you essentially are retransmitting the data that is up for retransmission. Setting of the retransmission timer is crucial. If the value is too small, unnecessary retransmission, timer too large, long waiting, degradation of throughput. So the problem is that delays in TCP, sender and receiver, there's no knowledge. TCP sender and receiver have no information from the network if they're located locally or they're different, no geographical information. That's why they have to figure it out. It's done adaptive using measurement, and that's another use of acknowledgements. TCP connections perform measurements of round trip times. Round trip time is the way to go and come back. Oh, sorry. Each TCP connection, each side, the sender, performs continuously measurements of retransmission time. And what it does is pretty simple. A segment is sent. When the acknowledgement for that segment is come back, that's a measurement. Then you're sending one packet, the acknowledgement for that packet comes back, that's another measurement. If a second packet is sent before the acknowledgement comes back for the first one, no new measurement is started. So you only measure one item at a time. You only measure, then you wait until that piece that you've sent out is being acknowledged. And this here is a cumulative add, so you just, forget about the three. I start a measurement here, I wait until the second segment is acknowledged. That ends the measurement, then you start it again, but then you don't wait until the first acknowledgement comes back. You wait until the data that has been sent is acknowledged. Yeah? So you have to, this says act for segment number 5, you know that sequence numbers are being sent, and you need to know what you sent the packet for. Yeah? That's it. Yeah? So that's the measurement rules. And then these measurements are used to compute a retransmission timeout. Now, how would you do it? If you're taking the round trip time, you're saying, well, retransmission timeout 3 times the round trip time, or 2 times the round trip time. That would be a reasonable value. 5 times, something like this. The issue, if you're taking the last measurements, the measurements have variance, you somehow don't, what you want to do is, you want to do the average over the last few measurements, something like this. Yes, does that make sense? You don't want to take, if you have a lot of, if the round trip time varies, and there can be a lot of these things here, like you're having delayed acts in there. This is not an exact. These are not exact round trip times for a packet. These are estimates. All these delayed acts, Miller's rule, they're all kind of distort the measurement. But overall, you don't want to take the latest measurements. You want to somehow average it. So what does one do? One uses a smoothing algorithm, and that's what TCP does. Yeah? It performs essentially an exponentially weighted moving average. And it's a complicated word for something very simple. I take the last measurements, I take that a fraction of this, like a quarter of the last measurement, plus I add 3/4 of my last value. So that the new measurement goes into the latest measurement goes into my data only with a weight of 1/4. So what's going on here is the round trip time measurements are smooth to generate a moving average. Yeah? Moving average. Moving average. And what we see here is actually exponentially weighted. Yeah. And we don't need to go on to this, you have an alpha there. So what you have here is, this is the latest measurement. FRTT is the smooth round trip time. So that's the average. So the new value of the average is the latest measurement that I took times alpha and the old value that I had before the measurement multiplied by 1 minus alpha, where alpha is a number between 0 and 1. Alpha is kind of this typical settings in TCP are 1/4. Alright, so that is a moving average algorithm. Then the guy who came up with this, do you know who came up with this? Van Jacobson. Van Jacobson came up with this. I actually just saw him when I was the week before classes started. I was at a workshop in Xerox Park in Palo Alto. He does other things now. But he's a crazy fellow, yeah? No doubt about it. He comes up with saying, well, this is not enough. If your network varies a lot, you should take into consideration the variations that you're serving. So if you see that your delays vary a lot, then you should increase your RTO value, because you want to account for the variance. Actually, no, that's very simple. But the thing is, this is all just done, because one person thought this was good, and it's just trial and error. There's no science behind it. This is all done by trial and error. The crazy part is afterwards saying this is the only way it can be done. So how does this end? This ended up in an implementation of the BSD software distribution, which then became the reference implementation, which then is kind of pretty much used by everybody else. Not necessarily, but these values then have been published in RFC's request for comment, that I showed you, of the IETF, and so this is then the default implementation. So there's a second value, which counts the variance of the round trip time, which counts the deviation from the average. So you're taking the measurement minus the smooth average, take the absolute value of that, so that's the deviation from the mean, and then you take the deviation from this average and do the same thing. You're taking beta, where beta is between 0 and 1 of the latest measured value, and then you're taking 1 minus beta of your smooth value. Alright, so these two variables are being taken place, are being accounted for, and then the smooth round trip time, the RTO value, this is the timeout value, is set to the average plus 4 times the variance. Why not 2? Why 4? Well, it's 4. So that's how this boils down to. And for the first measure, initially you don't have any measurements. The initial value for the RTO, look at this, is set to 3 seconds. Because initially you don't know what it is, so you set it very, very conservatively. Which leads to throughput degradation if you're having losses early on in a connection where you have sender and receiver close apart, but this obviously is long enough to cover a lot, so it's just set to a value that avoids unnecessary retransmissions in an early part of the connection. Yeah? Then the first measurement has no history, which is for this value for this value here we need history. Yeah? So what is just being set is the first value here. You set it sensibly to the RTT, the current measurement. That's my smooth value. and for the RTT to set it to half of the round trip time. That's the variance. So that's how it goes. All right, and so that's this. Now, if I'm actually almost done here. Now, the rule is, if you're doing retransmissions, you don't take measurements. The round trip time, if there are retransmissions taking place, no measurements are being taken. Why is that? Well, you don't, if you're having a segment, if you're having an acknowledgement for a segment coming back, you would not know if that is for a retransmission or the original submit. So we essentially say, once you're in retransmission mode, don't take measurements. Instead, for each retransmission, double the RTO value. This is kind of this exponential backup. Yeah? So, sorry. Keep on stepping on here. I'm sorry. Won't soon. So during retransmission, don't update the smooth RTT. So don't throw the measurements away. Each time when you retransmit, double the value. Do not go above 64 seconds. I mean, if you're in that game, then there's nothing. The connection is dead. If you're retransmitting a packet, really is 6-7 times. But it's complete. That's what your TCP connection is working on. You measure it; it's still running. You can, get this quite easily. So every time you're using the web and something gets lost, this is what's retransmitting and this is what's reading. All right. Now, so this is why do I have this? This is just the measurement, but that's what you're doing in the lab. So essentially, right? So next time we talk about TCP congestion control. I should have something. There's something funny going on with TCP congestion control in Linux implementation. But what I want to do is I want to cover the classical stuff first, and maybe next month we have time to talk about some of the recent advantages of what people do in Linux TCP, which does congestion control a little bit differently than what I discussed here. Okay, hope you enjoyed the lecture, and if you'd like to have some more candy.